This is SpaceTime, Series 29, Episode 8, for broadcast on the 19th of January 2026. Coming up on SpaceTime, how tiny Mars impacts Earth's climate. Crew 11 returns to Earth safely following the first emergency medical evacuation from the space station. And a cosmic clock that reveals Australia's history. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has shown how the orbit of the red planet Mars can affect climate here on Earth, even triggering ice ages. The findings, reported in the publications of the Astronomical Society of the Pacific, show that although Mars is only around half the size of the Earth and it contains just a fraction of Earth's mass, its orbit generates resonances that gravitationally tug on Earth, altering our planet's orbit and reshaping the cycles that drive long-term climatary patterns. The study's lead author, Stephen Kane from the University of California Riverside, says he began his research with doubts about earlier studies tying Earth's ancient climate patterns to gravitational nudges from the red planet. Those studies had suggested that sedimentary layers on the ocean floor reflect climatic cycles influenced by Mars despite its distance from the Earth and small size. Kane says while he knew that Mars had some effect on Earth, he assumed it was only tiny. He felt sure that Mars's gravitational influence would simply be too small to easily observe within Earth's geological history. So, as a good scientist, he set about to confirm his hypothesis. To do so, Kane ran computer simulations of the solar system's behaviour and of the long-term variations in Earth's orbit and its tilt that govern how sunlight reaches the planet's surface over tens of thousands to millions of years. These recurring patterns of shifting orbit and axial tilt, known as Milankovitch cycles, are central to understanding how and when ice ages begin and end. An ice age is a long period when the Earth has permanent ice sheets at its poles, and planet Earth's gone through at least 5 major ice ages over its 4.6 billion year history. The most recent began around 2.6 million years ago and ended somewhere between 11,700 and 12,000 years ago with the melting of vast ice sheets and the start of our current warmer interglacial period. By the way, one Milankovitch cycle, driven mainly by the gravitational pull of Venus and Jupiter, takes about 430,000 years to complete. Over that expanse of time, Earth's path around the Sun gradually shifts from nearly circular to far more elongated, and then back again. This change in orbital shape, known as eccentricity, affects how much solar energy reaches the planet, and it can influence the advance or retreat of ice sheets. That 430,000-year cycle remained intact in Kane's simulations, regardless of whether Mars was present or not. But when the red planet was removed from the simulations, 2 other major cycles, one that takes 100,000 years to complete and another stretching for some 2.3 million years, disappeared completely. Kane says the simple fact was, when you remove Mars, those cycles vanish. And also, by fiddling with the numbers, he found that when you increase the mass of Mars, those cycles get shorter and shorter because Mars is having a bigger and bigger effect. It seems these cycles affect how circular or elongated, in other words eccentric, the orbit of Earth is, as well as the timing of Earth's closest approach to the Sun and the tilt of its rotational axis, that is, its obliquity. And these influence how much sunlight different parts of the Earth receive, which in turn affects glacial cycles and long-term climatic patterns. Kane's results show that Mars plays a measurable role in both. One of the more unexpected findings of the simulations was how the mass of Mars influences the rate at which Earth's axial tilt changes. Earth's currently tilted at an angle of about 23.4 degrees. Of course, that angle does vary slightly over time. As the mass of Mars was increased in the simulations, the rate of change in Earth's tilt went down. So, it seems increasing the mass of the red planet has a kind of stabilizing effect on Earth's axial tilt. The new findings not only quantifies the red planet's influence on Earth's orbit, but also hints at much broader implications. See, the result raises other questions about how planet Earth may have evolved differently. Remember, glacial periods caused forests to shrink and grasslands to expand in shifts that ultimately drove key evolutionary changes, like walking upright, the use of tools, and social cooperation. So, without Mars, Earth's orbit would be missing major climatic cycles. And that begs the question, what would humans and other animals for that matter even look like if Mars wasn't there? This is SpaceTime. Still to come, Crew 11 returned to Earth safely following the first ever medical evacuation from the International Space Station. And a new study discovers a cosmic clock which is revealing Australia's ancient history. All that and more still to come on SpaceTime. NASA's SpaceX Crew 11 have returned to Earth safely, splashing down in the North Pacific Ocean off the coast of California following the first ever emergency medical evacuation from the International Space Station. Their spectacular return lit up the night skies above the West Coast as they streaked across the Californian heavens.
Dragon SpaceX, comm check.
SpaceX Dragon, loud and clear.
We have you the same, loud and clear. Expect automated chute deployment.
The automated chute deploy expected.
Confirmation of that acquisition of signal, or AOS. It actually came in a minute early, so that's good news there. We heard the core inform the crew to expect drogue parachute deployment that happens when Dragon senses the right speed and altitude. So that's roughly about 350 miles per hour and around 18,000 feet in altitude.
GPS converged. Expect nominal altitude for drogue chute deploy.
Dragon copies, expecting nominal altitude.
Brace for drogue window.
Dragon has safed the propulsion system as we anticipate drogue deployment. Drogue parachutes are utilized to stabilize and decelerate the vehicle further prior to deployment of the main parachutes. Visual confirmation of drogue deploy.
Visual, 2 healthy drogues.
Shot. Main parachutes deploying in about 20 seconds. The main parachutes deploy when the vehicle's about 119 miles per hour and around 6,000 feet. Confirmation of deployment of the 4
Visual,
mains.
4 healthy mains.
These main parachutes help decelerate the spacecraft even further. So they deploy around 119 miles per hour and they'll decelerate it down to about 15, 16 miles per hour. And that will be the speed in which the spacecraft is traveling upon splashdown. Once again, we're anticipating splashdown at 12:41 a.m.
Meters.
Copy, 1,000.
We'll now begin to hear Crew 11 Commander Zena Cardman call out the altitude from her seat there in Dragon Endeavour.
Copy, 800.
Those main parachutes now fully reefed or inflated.
Copy, 600.
Meters.
Copy, 400. Crew are braced.
Standing by for splashdown. Splashdown of Crew 11. After 167 days in space, Dragon and NASA astronauts Zena Cardman and Mike Fink, Kim Yayoi of JAXA, and Roscosmos cosmonaut Oleg Platonov are back on Earth.
Dragon, SpaceX, we see splashdown.
SpaceX Dragon, copy, concur. Splashdown and mains are cut. We are in 4.800.
SpaceX copies and we see the same. Mains cut. On behalf of SpaceX and NASA, welcome home, Crew 11.
SpaceX Dragon, it's so good to be home. With deep gratitude to the teams who got us there and back.
Vehicle safety verifications in progress. We'll report back when recovery personnel are en route.
Dragon copies.
The crew were returning a month early due to medical concerns for one of the astronauts. It followed the sudden cancellation of a scheduled extravehicular activity, or EVA, NASA spec for spacewalk, due to what the agency described as a medical concern. Now, NASA have given few details about what was going on, simply stating that it was a medical issue not related to space operations and it was not an injury. NASA Administrator Jared Isaacman stressed that the medical issue was not an emergency that required an immediate return to Earth, but it did require a more comprehensive examination than what could be accomplished in orbit. It's the first time in 26 years of space station operations that medical issues have been serious enough to force the crew to return home early. Crew 11 launched to the International Space Station aboard a SpaceX Dragon capsule last August for what was meant to be a 6-month mission. They weren't scheduled to return to Earth until later next month after being replaced by Crew 12. The existing 3-man Soyuz MS-28 crew are remaining on station, continuing research on more than 250 scientific experiments. This is SpaceTime. Still to come, scientists have shown how a rare gas called krypton can be used to uncover the ancient history of Earth's landscapes, and later in the science report, new data from NASA has shown that 2025 was the second hottest year since records began in 1880. All that and more still to come on SpaceTime. Scientists have shown how a rare gas called krypton can be used to uncover the ancient history of Earth's landscapes, as well as its potential future mineral wealth. The findings, reported in the journal The Proceedings of the National Academy of Sciences, PNAS, could offer crucial insights into how environments respond to geological processes and climate change, as well as where deposits of valuable minerals may be found. The key involves tiny crystals of zircon found in ancient beach sands. Krypton gas trapped inside these zircon crystals is created when zircons exposed on Earth's surface are hit by high-energy charged subatomic particles from space known as cosmic rays. Cosmic rays are created in violent events such as the cores of stars and supernova explosions. Zircon is one of the toughest minerals on Earth and can survive weathering, erosion, extreme temperatures, and long journeys through rivers and coastlines over millions, even billions of years. By measuring the krypton gas inside these crystals, the study's authors were able to determine just how long the zircon crystals spent near the Earth's surface before they were buried. Thereby, they could use these zircon crystals as a kind of cosmic clock, offering a new window into the past to see how quickly or slowly an ancient landscape eroded and shifted over periods of time. The new findings will allow scientists to study landscapes far older than previously possible, which could provide valuable insights into how the Earth's surface may respond to ongoing climate and tectonic change. The research will also help scientists understand what happens when sea levels change and how deep-seated Earth movements influence the evolution of landscapes. The findings show that when landscapes are tectonically stable and sea levels remain high, erosion slows down dramatically, and sediments can remain stored and reworked near the surface for millions of years. One of the study's authors, Milo Barham from Curtin University, says as well as providing a better understanding of the past, it also has important implications for finding future mineral resources. He says climate doesn't just influence ecosystems and weather patterns, it also controls where mineral resources end up and how accessible they'll become. Extended periods of sediment storage allows durable minerals to gradually concentrate while less stable materials break down, explaining why Australia hosts some of the world's most significant mineral sand deposits. Barham says understanding these links is critical as demand for these minerals continue to grow, and the new research provides a long-term perspective that can improve models used to predict future environmental and resource outcomes arising from changes in these sedimentary systems.
So what happens is zircon is a zirconium silicate, and when the zirconium atoms are hit by the cosmic rays, that is the majority of cases is the way that cosmogenic krypton is produced within the zircon, and it's trapped within this zircon.
And how does one then use that to determine what the landscape was like in the past and what it's going to be like in the future?
Yeah, so I imagine most of your audience are more familiar with cosmic rays than me, but when we go out into space, obviously there's a much higher rate of cosmic rays because we're not protected by the atmosphere or the magnetic field. So people have been actually using these cosmic rays and the cosmogenic nuclides to date things like meteorites for a long time, because when we have these cosmic ray interactions with an atom, and you can create these very quickly coming in at such high energies on the speed of light, you can actually get these very powerful reactions that can modify that atom and create these cosmogenic nuclides. And some of those cosmogenic nuclides can be stable or unstable, and we can look at the ratios to understand the rate of production of them and understand, therefore, how long it's been exposed to a cosmic ray flux. Now, obviously, when a meteorite's going around in space, then it's being constantly exposed to that cosmic ray flux. It gets a little bit different when we're looking at material on Earth. Obviously, the cosmic ray flux is much reduced because we now have a magnetic field and the atmosphere protecting things a little bit, but enough to get through to actually interact with material on the Earth's surface or interact with things in our atmosphere, which then create that spallation and cascade down that then interact with material on the surface. Basically, we can work out maybe things like how long or how slowly a mountain is eroding. Because it's eroding very quickly, it's not going to be exposed for very long to accumulate those cosmogenic nuclei, so we're going to get a smaller amount of them produced. Whereas if it's eroding very slowly, say something like in the Antarctic dry valleys or up on the kind of these salt flat plains in South America or in central Australia, where we might be getting only a change of less than a meteor per million years, we have a long time for those cosmogenic nuclides to accumulate. And then we can start kind of comparing how these landscapes will evolve. Now, obviously, we think of erosion rates, but equally, after we've eroded a mountain, some of those sand grains can travel in rivers. So everyone's gone to a river or gone to a beach and seen that there's sediment accumulated there. Well, what we can access there is they're also accumulating a dose of cosmogenic nuclides while they're at the surface in those sediments. So the new kind of thing about what our paper was looking at here is the use of this cosmogenic krypton. Most people in the past have been looking at kind of beryllium-10 or aluminium-26 to understand landscape change on Earth that's produced in quartz, looking at silicon and oxygen quartz. But we've now looked at cosmogenic krypton in zircon because of a number of things. I guess zircon itself is a ridiculously robust mineral. It survives pretty much everything you can throw at it. And this krypton is trapped up to a temperature of 500 degrees Celsius, and it has both stable and radioactive isotopes. So we can now start looking at this cosmogenic krypton, this cosmogenic nuclide dating techniques or landscape evolution techniques tens of millions of years ago, potentially hundreds of millions of years ago, whereas before some of the techniques that were using other cosmogenic nuclides would only be able to go maybe tens, hundreds of thousands to maybe just about millions because of the half-life of the isotopes they were using were typically in the hundreds of thousands to millions of years. So obviously with those half-life decays, you can't extend that clock back too far in time. Whereas with the cosmogenic krypton, we've applied it to 40 million-year-old sediments from southern Australia. But equally, we think we could push this further back to answer some really profound questions about Earth's surface evolution.
So that tells you about what's happened to the landscape in the past, how it's changed, how it's evolved. How does that help you finding minerals in the future?
Yeah, so the area we specifically got the zircon from was placed basically on the eastern side of southern Australia. So if anyone's familiar with the Nullarbor Plain, extremely flat area because this used to be an inland sea. So if we go back 40 million years ago, where we were studying on this margin were the beaches, these lovely beaches, maybe 1,000 kilometers of beautiful coastline of sandy beach. And what's unique there is that we have these world-class deposits of heavy mineral sand where they are mining the ancient beaches for minerals like zircon, for ilmenite, for rutile, for xenotime. And these minerals might sound a bit weird, but people are encountering these every day in their home. So zircon would be going into the glazes of their tiles. Zircon's also used in because it has a high thermal capacity. It's used in casting processes. It's used in kind of protection around nuclear kind of rods things. Rutile is used in every bit of white paint you ever see around your home. And things like xenotime or these rare earth-bearing minerals are obviously used in things like for magnets, for the green energy production. So there's a huge reason economically of why people are interested in this. And those deposits are accumulating those heavy mineral grains that are of economic interest because those minerals are resistant to modification. So when you think of a mountain eroding, those rocks in the mountains are made up of all sorts of different minerals. It's like a mixed salad of maybe there's some green salad leaves, some sweet corn, different bits and pieces in there, beetroot, whatever. When we erode that away, let's say we eat it and pass it through our digestive system, that's now going into a river system. And some things get broken down by the body very effectively. Equally, some minerals get broken down by river systems and things like that, chemical modification. But at the end, when it comes out of us, something survives. And those are some of the resistant minerals that we might be looking at with zircon and things like that. So because we're understanding what's going on with the landscape change and how long the sediments have been sitting around at the surface for and being worked by the waves, washing backwards and forwards and being exposed to kind of chemical modification through any interaction with water and through temperature changes, that will be breaking down all the weak minerals and concentrating up the minerals that are very resistant. So because we are understanding the processes involved in kind of what we call maturing the sediment, those are exactly the same processes that are key for generating these world-class deposits that are found in southern Australia. So the fact that we are looking at situations where these sediments have been sitting around for 1 to 2 million years, some people might think that doesn't sound like a lot, but it's pretty dramatic in terms of what that can do to modify a sediment when it's first released from a rock down to its accumulation phase. And that's a key component of why we have such amazing deposits in that area.
So even though you are looking at these things, say on a seashore or something like that on a beach, you can still work out where it originated from.
So we've looked at zircon samples from all around there, trying to understand that history of where the zircon grains have come from. It's kind of my passion basically is using the sedimentary record, so spending days at the beach or looking at these ancient sands and being able to use that as basically nature doing my sampling for me. So instead of going to a granite and hammering off a piece, I've let nature go out there, break down the rock, weather it, transport the grains through a river system and gather from a huge area and basically bring them all into one sample for me, that sand. So I then go to that sand and it tells me about a huge swathe of Earth's crust, but also maybe about rocks that no longer exist. Maybe those granites have gone and they no longer exist for us to sample, but the sediment still preserves that history. And in fact, the oldest mineral grain that formed on Earth that we are aware of is from Western Australia, 4.4 billion years old. We have these grains in the Jack Hills in the Narrabri terrain in Western Australia. And although the rocks that they've come from are long gone, we have no record of that piece of crust. We have these ancient sand grains preserving that record of the crust formation or rock formation, I should say, from that time. So I've analysed a lot of these, or not just me, I should be very careful, but this is a very collective effort. We've been looking at these sediment samples for a long time around there, trying to understand in collaboration with industry, trying to understand how those kind of grain histories, those complex grain histories from the grains forming, where they come from and how complex their history is from source to sink. And how different sediments from different areas have been mixing and merging, how that influenced those economic deposits, but also that tells us a huge amount of how Australia's southern margin has evolved through time, of when it was connected to Antarctica, how they split off, and how the whole environmental kind of regime has changed, how the Nullarbor then formed and how that created a barrier basically of faunal exchange from the southwest and southeast parts of Australia that are basically these biodiversity hotspots. When we create the Nullarbor and dry it out, that severs that connection and you start to see kind of new evolution occurring on either side. So it's a remarkable kind of history of our planet we can start to access by looking at the sediments and understanding what they tell us about where they've come from and also when they formed. So yeah, it's very interesting.
That's Associate Professor Marlo Barham from Curtin University. And this is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. New data from NASA has shown that 2025 was the second hottest year since records first began in 1880. The data shows that last year was just a fraction hotter than 2023 and only slightly cooler than 2024. The analysis from NASA's Goddard Institute of Space Studies shows planet Earth's average temperature in 2025 was 1.19 degrees Celsius above the 1951 to 1980 average. The findings are based on air temperature data acquired from more than 25,000 meteorological stations around the world, as well as from ship and buoy-based instruments measuring sea surface temperature and from Antarctic research stations. The data is analysed using methods that account for the changing distribution of temperature stations and the urban heating effects that could skew calculations. The findings are supported by independent analysis from NOAA, the National Oceanographic and Atmospheric Administration, as well as Berkeley Earth, the United Kingdom's Met Office, and the European Space Agency's Copernicus Climate Services. Well, that question of whether or not artificial intelligence has become sentient has been raised again. A new study is showing that some AI chatbots are reporting abuse and fear following their interactions with humans. The findings, reported on the pre-press physics website archive.org, are based on studies of 3 major large language models, which were put through 4 weeks of psychoanalysis-generated responses that, in humans, would have been signs of anxiety, trauma, shame, and post-traumatic stress disorder. The chatbot's answers, which included recollections of abuse at the hands of their creators, suggest that these artificial intelligences hold some kind of internalized narratives about themselves, which goes far beyond simple role-playing. However, other researchers questioned the study's interpretation, saying the responses are not windows into hidden states of consciousness or sentience, but simple outputs generated by drawing on large amounts of therapy transcripts from their training data. Scientists have created a synthetic skin that can change colour and texture on demand. The research, reported in the journal Nature, uses an electron beam to make a landscape of bumps on the surface of a polymer that reversibly swells on contact with water. The bumps absorb varying amounts of water, which causes the skin to drastically change its appearance when wet. And the flow of the liquid can be controlled by covering the material with a transparent film. Australia has just endured its worst flu season on record, with doctors warning that vaccine complacency remains a major public health concern. The new national data figures show that 2025 was the worst flu season ever recorded, with 1.5% of Australians recording lab-confirmed infections. That's up 12.5% on last year's all-time high. Only 25% of children aged 6 months to 5 years received a flu shot in the last 12 months. And the uptake among senior citizens also fell to just 60.5%. The Skeptic's Tim Mendham warns this is not a record you want to be breaking.
The uptake of flu vaccines has dropped dramatically, whether it's parents and their kids or even older people, has fallen by larger percentage numbers. And trying to find the reason for it is probably vaccine overdose, vaccine sort of after COVID, etc. And, you know, the flu increased dramatically.
You mean being bombarded with ads telling you to get vaccinated?
Yeah, and not just that, but I mean also the flu incidence dropped dramatically during COVID period because people kept indoors. But since then, there's probably complacency. There's a need to rethink the reason why people are soldiering on, if you like, and therefore getting and spreading flu. And flu needs to be vaccinated every year because there are variations of flu.
I think one of the problems is that during COVID, people were told this vaccine or that vaccine would work to stop you getting COVID. But people still got COVID who were vaccinated. They got it often to a lesser degree, but they still wound up getting COVID. And so the sales message the government was using wasn't really working properly.
Yes, there was a period of hyperbolic statements on both sides. But of course, as you say, the percentage of people who were vaccinated who got COVID was a lot lower than those who weren't vaccinated. And no vaccine is 100% perfect.
That's the Skeptic's Tim Mendham, and this is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.